How would you describe to someone exactly where you lived? I'm guessing you would start with your address. When you specify the location of a building, you usually list which country it's in, which city and state it's in that country, and its street address. Just like no two buildings have the exact same address, no two electrons can have the same set of quantum numbers. Also, there are very specific rules about quantum numbers that can exist together, just like you wouldn't say that Wisconsin is a state in the country of Spain. A quantum number describes a specific aspect of an electron. Just like we have 4 ways of defining the location of a building, country, state, city, and street address, we have 4 ways of defining the properties of an electron, or 4 quantum numbers. Before starting this lesson, you should have an understanding of what an electron configuration is and how to write one for an element. Remember that an electron configuration tells us where each electron is in an atom, and knowing the arrangement of the electrons is necessary in order to understand how an element will react and what types of molecules it will form. So let's start with an atom of silicon. What would its electron configuration be? You should have an answer of 1s2, 2s2, 2p6, 3s2, 3p2. Silicon has a total of 14 electrons, which are all represented by that electron configuration. So what do all those numbers and letters mean? This lesson is going to crack that electron configuration code. Before we go into great detail about those quantum numbers, it is important to note when I say location, I mean probable location. There's really no way to know exactly where an electron is at a given time. They're very elusive. But it is possible to determine which specific 3-dimensional region it is probably in. These 3-dimensional boundaries where an electron is most likely found is called an atomic orbital. The first quantum number that describes an electron is called the principal quantum number, and it is often symbolized by the letter N. This number tells us the energy level or size of an orbital. The higher the number, the larger the region is. So let's take the electron configuration for silicon and look at the very last electron that was added to silicon. It should be one in the 3p orbital. That 3 indicates the principal quantum number. So for this electron, n equals 3. The orbital that the last electron is going to be in will be larger than the 2p orbital because it has a higher number. This means that the 2p electron is more likely to be found closer to the nucleus than the 3p electron. You will also hear the term energy level a lot when dealing with electrons and their locations. The 2p electrons are located in the 2nd energy level, and the 3p electrons are located in the 3rd energy level. They will have more energy than the electrons in the 2p orbitals. So in silicon, how many electrons will have n equals 3 as one of their quantum numbers? The answer is 4. There are 2 3s electrons and 2 3p electrons. All start with 3, so all will have a principal quantum number of 3. The next quantum number relates to the letters in the electron configuration. Which letters did you encounter when you wrote out electron configurations? You should have encountered S, P, D, and F. The letters represent the angular momentum quantum number. It sounds like a mouthful, but it's really just the shape of the orbital, and it's sometimes symbolized by the letter L. S orbitals have a spherical shape. P orbitals are sort of dumbbell shaped. D orbitals look similar to a 3-dimensional 4-leaf clover, and F orbitals have more of a flower shape. When assigning a number to each shape, the S-shaped orbitals have an L equal to 0. The P orbitals have an L equal to 1. The D orbitals have L equal to 2, and the F orbitals have L equal to 3. So that last electron that we added to the silicon atom in the 3p orbital will have an L equal to 1 and be sort of dumbbell shaped. So for this electron, the N equals 3 and the L equals 1. You may notice that some combinations of quantum numbers are going to be impossible. For example, you can't have N equal to 1 and L equal to 2 for a cluster of quantum numbers, because that would mean that the electron configuration would have to be 1d, and there are no 1d electrons. The next quantum number indicates the position of the orbital, how it's arranged in space. It is called the magnetic quantum number, and it's sometimes symbolized by ML. No matter how many times you try to rotate a sphere, you will always end up with only one orientation. This means that there is only one magnetic quantum number possible for all the s orbitals. That is, ML equals 0. The p orbitals can have 3 different orientations, so they're assigned 3 different magnetic quantum numbers for the possible positions of the p orbitals. We have ML equals -1, ML equals 0, and ML equals +1. The -1 means that the dumbbells are aligned along the x-axis. The 0 indicates that the dumbbells are aligned along the z-axis, and the +1 indicates that the dumbbells are aligned along the y-axis. The d orbitals and f orbitals are a little bit more complicated, but know that the d orbitals can have 5 different orientations: -2, -1, 0, +1, and +2. And the f orbitals can have 7 different orientations. So the different positions of the f orbitals are represented as -3, -2, -1, 0, +1, +2, and +3. That last electron that we put in the silicon atom would have an N equal to 3, an L equal to 1, and an ML equal to either -1, 0, or +1, representing the 3 possible positions the p orbitals can have. The final quantum number doesn't deal with size, shape, or position of the orbital, but the actual electron itself. The spin quantum number, often symbolized by S or ms, deals with the spin of the electron and plays a very important role in determining the magnetic properties of an atom or molecule. Each individual orbital can hold up to 2 electrons, and each electron will have a different spin, represented as either +1/2 or -1/2. So for our silicon electron, it would have an ms of +1/2 or -1/2. There's really no way to tell just by looking at the electron configuration which one it is. Okay, now we're going to do a little practice. Write out the electron configuration for calcium. You should have 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2 as an answer. We are going to focus on just one of the 2 4s electrons. One of these electrons should have a series of quantum numbers like this: n equals 4, L equals 0, 0 is the number associated with the s orbitals, and ML equals 0. There's only one way to orient a sphere. ms will equal either -1/2 or +1/2. Whichever spin this 4s electron will have, the other will have the opposite spin. Understanding the quantum numbers can be quite difficult because it's such an abstract concept. You never actually see electrons in your daily life, so it's not easy to relate to. What helps is thinking of a quantum number like a piece of an address, each getting more and more specific. The principal quantum number just indicates the size of the orbital or the energy level. The angular momentum quantum number indicates the shape of the orbital. The magnetic quantum number indicates the orientation or position of the orbital. And the spin quantum number indicates the spin of the electron, represented as either +1/2 or -1/2. Remember, an orbital is just a 3-dimensional location around the nucleus of an atom where an electron is probably going to be located.